Hello, congratulations, you've made it to part 3 of the respiratory system, where in this video we will really focus on looking at how oxygen and carbon dioxide is moved between the various types of respiration. And so how does oxygen and carbon dioxide move within external respiration, and how does oxygen and carbon dioxide move within internal respiration? Remember that internal respiration is the interplay of exchange between our blood vessels and the tissues. And so how is oxygen released into the tissues, and how is carbon dioxide moved into the blood vessels? And with external respiration, we see the interplay between the blood vessels and the alveoli. And so how does oxygen move from within the alveoli into the blood, and how does the blood then release carbon dioxide into the alveoli to be expired during the process of expiration? And so with that, let's go ahead and let's jump in. And we start with a couple reminders. These are reminders that should not be anything new and earth-shattering to any of you. You should be well aware that, like most things within the body, when we're dealing with any kind of passive transport, like this is, the movement of oxygen and carbon dioxide, we are dealing with the movement of, in this case, a gas down its concentration gradient. So in other words, moving from an area of higher concentration to an area of lower concentration. So oxygen is going to move from where there's a higher pressure gradient or concentration gradient. And really, that's probably a better way of looking at this. Now that I'm looking at this, instead of dealing with concentration, we're probably better off to deal with looking at this in terms of not concentration, but pressure. All right, and so these pressure gradients, right, are based off of the partial pressure of each gas. So oxygen is going to move from an area of higher pressure to an area of lower pressure. Carbon dioxide is going to move from an area of higher pressure to an area of lower pressure. The only caveat to this, is that these gases actually move across a watery barrier. And so there is this little layer, buffering layer, if you would, of water that surrounds the alveoli, that kind of separates the alveoli from the blood vessels. And so how exactly do the gases deal with that? Because gases diffuse differently through air than what they do through water. And the ability for the gas to become soluble or dissolved within water is very different than how it's diffused through the air. So we've got to look at that. We need to look at that. And so we will look at that. Solubility, once again, is the ease by which a gas dissolves into a solution. And in this case, the solution is primarily water. There's always some other things in there, but it's primarily water. And the key here to remember is that the ease by which a gas will become soluble depends largely on the pressure of the gas. And so when we talk about low pressure equals high solubility, what we're talking about here is low pressure within the fluid. All right, and so when the fluid is experiencing lower pressure, then gas is more soluble. And when that fluid is experiencing higher pressure, that the solubility, or the ability for that gas to dissolve within that fluid, decreases. Think about those of you that like to go fishing. Think about when's the best time to go fishing? If you're doing freshwater lake fishing, freshwater fishing, All right, when's the best time to go fishing? 6 a.m., 1 p.m., or 6 p.m.? All right. Chances are you're going to select 6 a.m. and 6 p.m. or 7 p.m. or 8 p.m. Why? Because it's cooler. Right, well, what does that mean? Well, what that means is that water has cooled, it's expanded. There's more space between the molecules. Pressure is overall lower within that body of water, which means gas is more soluble. There's going to be more oxygen available in that water. The fish are going to be more active. If you go at 1 o'clock in the afternoon or 2 o'clock in the afternoon, there's a lot of thermal energy that is contained within the hydrogen bonds holding the water together. And what that does is it forces those molecules to be more compact. Adhesion increases, which increases the pressure. When you increase the pressure, you kick the water, you kick the gas, the soluble gas out. And so your oxygen contents are, your oxygen's actually lower. Oxygen does not dissolve or is not as easily soluble in water as some other gases. And we're going to look at that. Carbon dioxide is 20 times more soluble in water or in aqueous solution than what oxygen is. And so there's some things that we need to consider. But the fish are not going to be as active at 1 o'clock or 2 o'clock in the afternoon because there's higher pressure within that water. Oxygen is less soluble. There's not as much oxygen available. And if they're going to be metabolically active, they need a higher amount of oxygen. So you're not going to catch as many fish 1, 2 o'clock in the afternoon as you will at, let's say, 6 a.m. or 6 p.m. Because of the solubility and the availability of the gas. And as I mentioned, the gas must travel across this thin watery membrane that is surrounding the alveoli and separating out the capillary beds. And this becomes an issue because oxygen and carbon dioxide diffuse differently. They have different solubility factors between the two of them. We call this interface between the alveoli and the capillaries and this watery layer that surrounds them is what we define as being alveolar gas exchange. And so you've got your alveoli. Hold on one second here. Here's your alveoli right here. All right, there's your alveoli. Surrounding that alveoli, you've got this watery barrier. And then you've got your capillaries that are then surrounding that. And so oxygen needs to be able to move from the alveoli into the vessels. And as they do that, they are crossing that watery membrane. Well, again, oxygen doesn't diffuse, isn't as soluble in water. And so what happens is within the lining of the alveoli, you've got alveolar cells. You've got type 1 and type 2. Type 1, type 2 alveolar cells. And it's these type 2 cells that will secrete something called surfactant. And what surfactant does is surfactant lowers lowers the pressure within water. In other words, it makes it, it reduces cohesion and adhesion. Right? This ability for water molecules to stick to itself. It reduces that, and by reducing that, it allows for the oxygen to go ahead and more easily become soluble within there. Reduces the pressure, lowers the pressure by reducing cohesion and adhesion, which increases the solubility of the particular gas that you're trying to move. In this case, the gas that we're trying to move is oxygen. Carbon dioxide we don't worry about as much, because carbon dioxide is again about 20 times more soluble than what oxygen is. And that's what this is what we're kind of getting into right here. Right? So if you've got a container, right, and the container is surrounded by air, within that air, let's just say the partial pressure of oxygen is 100 millimeters of mercury. Right? That's just how much pressure is there. The water, right, this container of water that the air is surrounding has no free oxygen, no oxygen gas, O2, atmospheric oxygen present in it. So its partial pressure is 0. As the air bounces off of the surface of the water, oxygen molecules can be exchanged. Right? Oxygen will move from the air and into the water, and back from the water back into the air in the to try to achieve equalness, to try to achieve the sense of concentration equality with pressure. Right? So pressure becomes equalized in the air and in the water for the partial pressure of oxygen. It might only take 2 molecules of oxygen to go into the water for it to have a concentration, to have a pressure of 100 millimeters of mercury. And so once the pressures have become equalized, oxygen will not move between air and water anymore. That's not as effective. And so what surfactant does is surfactant lowers that overall pressure within the water that's created by the water molecules sticking together, so that more oxygen molecules can be transported across that watery barrier. Again, because pressures are going to be equalized. It's not so much concentration. Right? We're not going to sit there and say we've got 30% oxygen here, and so therefore we need 30% oxygen here. That's not the case. Right? It's millimeters of mercury. Once the pressure is equalized, gases will no longer flow. Right? And so that's kind of what this here is showing on this diagram. So if we follow this, right, here's my initial container that I was just talking about. Here's my container of water. It's got 0 millimeters of mercury of oxygen, right, in there. Right? And here's my molecules of oxygen in the air. Right? Partial pressure of that oxygen within this scenario is, let's just say, as 100 millimeters of mercury. Well, these oxygen molecules are banging around. Right? They're moving. Right? And every now and then, one of those oxygen molecules will go ahead and actually move into the oxygen or into the water. And the key is the oxygen will move until the pressure is equalized. Right? And these oxygen molecules are going to be banging around in here as well. And that's what you're seeing here. Right? Maybe it only took 5 molecules to equalize the pressure, but the pressure is equalized. All right. So it's not a concentration. It's not a percent of molecules. It is a pressure that is being created. The oxygen is now equalized as far as pressure. All right. So with that, oxygen is less soluble than carbon dioxide, and I think I mentioned that before. Carbon dioxide is about 20 times more soluble than oxygen. Now, why is that important? Well, it's important for basic physiology. All right, carbon dioxide has a higher emphasis of being uh, disposed of. Right, so carbon dioxide is an acid. It lowers pH, makes more acidic. Right, so it's going to make the blood more acidic. So there's a greater emphasis on getting this out. Well, we transport, the majority of the carbon dioxide is actually transported, and we're going to talk more about this later. The majority of carbon dioxide is transported within plasma. And we already know that plasma is 95% approximately water, 95 to 98%. All right, water. And so carbon dioxide very easily diffuses into the plasma. With that, once that carbon dioxide reaches the lungs, it very easily diffuses across that interface, right, between the capillary and the alveoli as it crosses that water, because there is such an emphasis on trying to get rid of that carbon dioxide. It's imperative. Oxygen, right? Remember, each oxygen molecule can hold something. What was it? What did we calculate out? 2.8 billion molecules of oxygen can be held on each red blood cell. All right, so yeah, we have to replenish that oxygen as we're using it, but there's always some oxygen that is there, and so that urgency is not as bad. Surfactant helps that because surfactant lowers that overall surface tension that is being created by the water molecules sticking together. So it allows oxygen some more freedom to dissolve across that barrier. But it's still more important for us to get rid of the carbon dioxide, because if a person experiences acidosis, where the pH of the blood drops below 7.35, right, once it gets down into about 7.2, 7.1, you start to get confusion, you start to get incoherency, you start to pass out, you can go into a coma, you see spots in front of your eyes, you lose your equilibrium. All of these things begin to happen. And so it is, again, critical for that carbon dioxide to be removed from the body. So it is beneficial that it is 20 times more soluble than what the water is. And this can all be summarized in what we define as being Henry's law. Right? So Henry's law simply says that at a air and water interface, for a given temperature, the amount of gas that dissolves in the water is determined by its solubility in water and its partial pressure in the air. So for a given gas, what is its solubility within the water? That's a predetermined value. When we look at that in light of what is the partial pressure of this gas in the surrounding atmosphere, that will tell us the ease at which that gas will become soluble within that given fluid. And so Henry's law kind of is what we've been looking at. What are the factors that influence a gas's ability to become soluble? And then there's some other things that we need to consider here. Henry's law takes this all into account, but there are some other factors that we need to consider. Surface tension is one thing. What we define as being lung compliance is another thing, and we're going to talk more about this, so don't jot this down yet. But airway resistance, all of these things kind of influence this idea of Henry's law. It will influence the partial pressure of oxygen within the alveoli, which will go ahead and influence its ability to truly be soluble at its maximum capacity within, as it's crossing from the alveoli into the capillaries. And so there's some things that we need to look at that. In the lungs, it should be noted that Carbon dioxide is unloaded and oxygen is loaded. This is in the lungs. All right? But at the tissue level, it is actually the opposite. In the tissues, oxygen is unloaded and CO2 is loaded. And so it's reversed. All right, so I did want to make that distinction on this slide right here. So let's spend a few minutes. Let's talk about what are the physical factors that will influence a gas's ability to become soluble across this air-water interface that we see between the alveoli and the capillaries. And how does that impact pulmonary ventilation? How does this impact external respiration within the lungs? And so the biggest thing that we have to overcome is surface tension. All right. This idea that water molecules have this natural attraction to one another. And as they cling together, it increases the pressure within the fluid, which makes it harder for a gas to become soluble. And when you're dealing with a gas like oxygen, which is already has a high resistance to solubility, having this higher surface tension is further going to reduce that. And so we need to consider how do we overcome this? And the answer to that is surfactant. And so we're going to talk a little bit more about that on the next slide. But again, other factors to consider here besides just surface tension, other factors that we need to consider are airway resistance. Right? In other words, what's the diameter within the bronchioles? And this mainly impacts the bronchioles. The bronchi don't have the same kind of influence or impact on airway resistance as what do the bronchioles do. And so when you're dealing with things like COPD, when you're dealing with things like asthma, anything that is going to reduce the ability for air to reach the lungs, what you're dealing with is bronchial constriction or bronchial dilation. Again, within the bronchioles. And so as they constrict because of an irritant or a spasm or a contraction or something, you're going to reduce the amount of air that's going to reach the lungs, which is going to reduce partial pressure of the gas, which is going to reduce the ability for that gas to become soluble within the water and make its way into the capillaries. And so that's one thing that we need to consider. The other thing that we need to consider here is lung compliance. And when you deal with lung compliance, you're really dealing with the ability for the lungs to expand. Lung expansion and relaxation. Under normal circumstances, this is all regulated. This is all regulated through the intrapleural pressure. So go back to what we were talking about in the last video, that we know that the intrapleural pressure is about 754 to 756 millimeters of mercury. Atmospheric pressure is 760 millimeters of mercury. And so you have this negative pressure, and that negative pressure pulls on the visceral pleura, which helps to keep the lungs expanded. Well, in some diseases like COPD, chronic obstruction pulmonary disorder, In some of those diseases, what ends up happening is you lose the ability for recoiling within that lung tissue, and so the elasticity decreases. And so you take a deep breath in, you drop the pressure within the lungs, within the pulmonary. The pulmonary pressure reduces, but what ends up happening is as the diaphragm relaxes and as the external intercostals relax, the lung tissue itself does not relax. It stays expanded. Well, you're functioning at a lower pressure now as the baseline. And so what happens? You've got to try to take a deeper breath in to try to lower the pressure in the pulmonary pressure within the lungs. That's lung compliance. All right, so the lungs are not recoiling to go ahead and go back to basically a starting position of 760 millimeters of mercury. It's starting lower. Right? It's almost like COPD. Think of COPD as being a sea level version of being in Denver. All right, to where it's a disease because that's not the normal state, and it's chronic. It is definitely chronic. And so when we look at things like surfactant, right, surfactant specifically deals with the surface tension found within and surrounding the alveoli. And again, as I mentioned, what it does is the surfactant is secreted from type 2 alveolar cells. We kind of mentioned that. You can see that listed there on the diagram. And what it does is it basically lowers the surface tension of the water surrounding the alveoli. And the reason why that is important is because of the higher pressure of cohesion and adhesion, what ends up happening is the alveoli would actually end up collapsing on itself due to the pressure. And so surfactant reduces that overall pressure, prevents the alveoli from collapsing, and reduces the resistance to oxygen being able to go ahead and become soluble, moving from the alveoli into the capillaries. And you can see on this slide, you can see here's a capillary right here, there's a capillary right there. And so these capillaries are very close to the alveoli. They're all scattered throughout. And you can probably, you've even seen that in some of the histology that I've posted up on Canvas. Other factors that will influence oxygen loading and unloading, or carbon dioxide loading and unloading, is the amount of time that the red blood cell is spending within the capillary. The average time that it takes to load and unload a molecule of oxygen or molecules of oxygen is about a quarter of a second. Right, so we can load and unload oxygen and carbon dioxide in about a quarter of a second. And those red blood cells are spending almost 3/4 of a second within the capillary surrounding the alveoli. And that's reduced to about 1/3 of a second during exercise, but 1/3 of a second is still more than 1/4 of a second. And so there's still plenty of time for the body to go ahead and load and unload the oxygen and the carbon dioxide. And so I want to kind of wrap up here with just a quick look at gas exchange that happens both with external respiration and internal respiration. And to understand this, we have to understand what are the normal pressures that we're dealing with. And so the partial pressure of oxygen within the alveoli tends to be about 104 millimeters of mercury. Right? Now that's alveoli. All right. The blood return to the lungs, right? So this is the venous blood. Right? This is the blood that has now been circulated. It's come back into the right atria and the right ventricle, and it's now left the heart through the pulmonary arteries, which are carrying less oxygenated blood. The partial pressure of oxygen within that blood returning to the lungs is about 40 millimeters of mercury. And so follow the math here. All right, we know that oxygen is going to move from an area of higher pressure to an area of lower pressure. What does that mean? Well, this means that 104 millimeters of mercury partial pressure of oxygen in the alveoli is going to cause oxygen to move from the alveoli into the blood. Right? We're going to do what we call oxygen loading at that point in time. Right? As that blood leaves the lungs, it returns to the left side of the heart and it's pumped out through the aorta. What we see is the intracellular partial pressure of oxygen. In other words, the partial pressure of oxygen in the tissues is about 40 millimeters of mercury. Right? But the arterial blood that is arriving within those capillary beds is actually about 95 millimeters of mercury. And so what ends up happening? Again, oxygen moves from an area of greater pressure to an area of lower pressure. So oxygen unloads in the tissues. That oxygen is going to move from the capillary and make its way into the tissue. And what does this all look like? Well, this is what it looks like. All right, so let's go ahead and let's kind of follow this. All right, right now we're following this pathway here. All right, so the air comes in. We know that under normal circumstances, the partial pressure of oxygen is 160 millimeters of mercury coming in from the atmosphere. All right, that alveolar pressure decreases partial pressure of oxygen to 104 millimeters of mercury. All right, the blood that is returning to the lungs is coming in at partial pressure of oxygen in the deoxygenated blood or less oxygenated blood is 40 millimeters of mercury. And so this blood is returning into the lungs. When it gets into the lungs, that oxygen moves from 104 down to the 40. And so it loads into the capillaries. That blood is returned to the heart, comes up into the aorta, and it is distributed systemically, where that blood is now has a partial pressure of oxygen of 95 millimeters of mercury. It makes its way into the capillary beds where the tissues, right, the intracellular pressure is about 40 millimeters of mercury. And so here we've got oxygen unloading because the blood has a partial pressure of oxygen of 95. The tissues has a partial pressure of oxygen of 40. Right, of 40. And so oxygen is unloaded within the tissues. Now, the flip side to that is what is happening with carbon dioxide. And we're going to look at this more in the next video. But in carbon dioxide, right, what is happening is just the opposite. So where O2 is loading in the lungs, CO2 is unloading. Why? Because the partial pressure of carbon dioxide is 46 millimeters of mercury in the blood returning to the lungs, but that same partial pressure of carbon dioxide within the lungs is 40 millimeters of mercury. So again, we're going to move from an area of higher pressure to an area of lower pressure, so that carbon dioxide is unloaded. And in the tissues, we see just the opposite. In the tissues, we see a partial pressure of carbon dioxide at 46 millimeters of mercury, right down here. But in the arterial blood that is arriving into those tissues, the partial pressure is 40 millimeters of mercury. And so again, we see a loading of CO2. All right, we're going to explore this a little bit more in the next video, kind of give you some more visuals of how this all looks. But I think you've had enough now to overwhelm you a little bit. You're probably hyperventilating a little bit. Your rate of respiration is increasing. You're probably panicking. Carbon dioxide is leaving your body at an accelerated rate. And you need time to digest all of this material. And so I'm going to give you some time. And I hope you have some questions for me. I'm always willing to answer those questions, and so go ahead and fire them off. And until then, I'll catch you on the flip side.